So the floor is yours.
Okay, thank you. So I will talk about phase vectors of a rainbow simplicial complex. So I will try to mention some words which may be more similar to the audience, say later. So we call the definition of a phase vector. So we have a simplicial complex that's just a family of sets which are closed under taking subsets or a downset in the Boolean algebra. So then we can look at the number of subsets, number of sets in data which are of size I. That is, for any non-negative integer I, we use data sub I for those elements of data of size I. And we call them I phases of the simplicial complex. So in topology, usually they will call it I minus one phases. They use the dimension as the parameter, but here we use the cardinality of the set as a parameter here. So if data sub k is non-empty, but data sub k plus one is empty, then we call this sequence the phase vector of data. We don't need to count data k plus one, etc., because they are all equal to 0 by our convention. And we call the top term here in the phase vector data k, the size of data sub k, the size of this complex data. So this is a very easy combinatorial concept, phase vector of a downset in a Boolean algebra. But many research are devoted to the understanding of phase vector. We copy some words from basically a survey paper by Biner and Bjorner. So they say that many constraints of a combinatorial or topological nature, they govern the instant structure of a CL complex. And then we need to understand the instant structure, which are governed by some constraints. But it's not easy to say we have a good understanding of something, but maybe we can say something on the F vector, because this is a very simple concept. Everyone can understand, but there are some challenging problems there. We will start from some very easy one later, but before that, we introduce some notation. Elementary symmetric polynomial. We use sigma n for the nth elementary symmetric polynomial. And then we use tau n for the variant of sigma n. Here, tau n applied to b1 up to bn equal to sigma n applied to b1 minus 1 to bn minus 1. So this will be an important function for this talk. Also, we use this notation. So we use square bracket for the first n positive integers. We use this notation for the first n plus 1. For the smallest non-negative integers from 0 to n. So there are some difference between these two notations. After this, we can look at a very easy example. We look at a graph. Suppose that we have a graph with A vertices. You can say vertices are just the one faces of this one-dimensional complex. Then we look at the second term or the third term in the phase vector. That's the number of two faces or the number of edges. Surely it's at the most A choose 2, very easy. This is trivial. If we have some constraint on the graph G, say it is n partatile. This means that you can color the vertex of G using n colors. So here, coloring is the usual coloring used in graph theory. So if this graph G is n partatile, and if we know that the partatile sets have sizes A1 up to AN, then surely it's also trivial that the number of edges or the number of one faces at most is bounded, upper bounded by this number. This is just the second elementary symmetric polynomial of the given parameter A1 up to AN. So this is some kind of constraint. So comes from, say, coloring. we can look at some other constraint. Suppose this graph G is a forest. You can say, because there are many characterization of a forest using homology, using various kind of language. And then you can find a very kind of generalization of this result. So for a forest, you know the number of edges at the most A-1. That's just tau 1 applied to A. So the question here, how to generate all these three results to generate simplicial complex. So the problem includes how to generalize, how to define a forest, how to define n patatype, etc. So we look at the simplicial complex. So these are very famous results. Kuska-Katerna theorem. Basically, these results characterize the phase vector of simplicial complexes without any constraint, as long as it is a downset in the Boolean algebra, and we want to look at its phase vector and see is there any characterization. Basically, they say Boolean algebra is a Macaulay poset, and so basically they use this Macaulay function from this representation to this representation. You just decrease k to k-1, k-1 to k-2, etc. This is very much the same like here, from A-2 to A-1. So the first item is just a very special example of the Kuska-Katerna theorem. So we see that for the first trivial result, we have a very good generalization. Surely EKR follows from Kuska-Katerna because in this workshop, there are several talks devoted to EKR. In general, we have the question. So suppose we have a simplicial complex data, we partition its vertex set or one faces into, say, n parts or color classes. And the sizes are A1 up to AN. So we have this parameter. We want to use this parameter to give an estimate of the phase vector of the simplicial complex. Surely we also want to impose some more constraint on the complex besides this A1, AN, besides this constraint. So the other constraint maybe we want to, in this talk, we want to understand those tree-like complex. So there are many meanings, many possibilities for tree-likeness. So basically we will focus on collapsibility and sparsity. So from these two viewpoints, we try to define tree-likeness. So there are already some results, some earlier results. So if we only have the coloring constraint, so Frankel, Freud, and Carlyle, so already in 1988, they obtained the colorful Kuska-Katerna theorem. Basically, they show that for the general Boolean algebra is also a Macaulay poset, and so they can characterize the phase vector of a rainbow simplicial complex. But the Macaulay function looks to be very complicated, and so you do not expect to have a formula like this, very clean formula, because for the general Boolean algebra, the Macaulay function too complicated to really write to be written down. Alone and Carlyle in 1984, they have an upper bound estimate for the phase vector of T collapsible simplicial complexes. So they impose constraint on the collapsibility. But for this result, they do not consider coloring. But for this FFK theorem, they impose some constraint by coloring. They use the parameter of the color classes. So none of these two results are an answer to our question, because in our question, we want to combine the two constraints. We want to see what can be said. So let's introduce collapsibility more carefully. So this is really a combinatorial concept. This stems from simple homotopy theory by Whitehead. Take a phase X from the given complex data. We can try to do some operation, maybe elementary small operation. This is called elementary collapsing or topological collapsing or animated T collapsing. We have various names for that, but this operation is very easy. You just remove X and all its cofaces. Basically, we want to still get a complex, a simplicial complex, but we do not want to see this X in the new complex delta prime. So if we remove X, then we have to remove all its cofaces. So this operation is called elementary collapsing if all those cofaces of X, among these all faces, there is a unique maximum one. Basically, we are removing a Boolean algebra. Then we say this operation is an elementary collapsing. And this elementary collapsing is even called a topological elementary collapsing if this interval is non-trivial. We are removing this interval, this Boolean algebra. This Boolean algebra contains more than one element. Namely, X is not equal to Y. The bottom element X is not equal to the top element Y. And we call this collapsing a T collapsing if the bottom element X has a size at the most T. If we are doing a sequence of, say, topological T collapsing, these are a sequence of elementary collapsing, then, in each step from delta I to delta I plus 1, then we say we go from delta 1 to delta n by a T collapsing or a topological T collapsing or just a collapsing. Basically, a sequence of elementary collapsing is a collapsing. So whenever we can do a T collapsing to make the given complex data to the empty one, we say this complex data is collapsible or T collapsible or topological T collapsible according to which kind of elementary collapsing we are using. So there are lots of study on this operation. Let me say that complex is a TD tree, provided we can do T collapsing from data to a simplicial complex delta prime, which does not have any D faces. For collapsible, we mean we can go from the given complex to the empty complex. All the faces disappear. But for a TD tree, we only want to kill those faces of size at least D. So all those faces should be killed. If that can be done, we say the given complex is a TD tree. So basically, in the last few slides, I am trying to explain what's the so-called tree likeliness or collapsibility constraint on the complex. And then I am talking about the coloring constraint. Basically, this is just to give a coloring of the one skeleton of the simplicial complex. So it is very easy. I don't need to really explain anything, but we need some terminology. That's why I still write several more slides here. So I talk about an n color set. So an n color set is just a sequence of n disjoint non-empty sets. You can think of this as a coloring of the ground set. So S1 is of color 1, Sn of color n. So I use this notation just for the convenience of describing our results. And we call the union the ground set, and I will also use this this notation. And we name this sequence the size of each color class, this sequence the type of the n color set. And then if we have an n color set, then we can look at those subsets. The subset should be so-called K-rainbow subset. So this so-called K-rainbow subset is a subset of, you can say a subset of the ground set of S, which of size K, such that it is really colorful. So in this set X, so any two different elements from X should have different colors. For example, here we have say here. So this is red plane. We have 2 red plane and 3 blue planes. So this is a type 2-3 color sets. And then all the rainbow subsets can be described just by this grid set. Say here, this plane. You can say this plane has a blue plane, a Y3, and a red plane, X2. You can also look at this plane in the grid. So this is just of size 1. This set only has the blue plane Y1. And also look at here. This is the empty set. So the set of all rainbow sets basically just generate Boolean algebra, because when all the parameters are equal to 1, so go back to the usual Boolean algebra, just a hypercube. But here we have a general high dimension grid plane set. And then we can look at rainbow symmetry complex. As I said before, this is a very easy concept, just a symmetry complex, and we will try to assign a coloring to the one skeleton of the symmetry complex. Then we have a rainbow symmetry complex. But if we we use this kind of language, it's not very easy for us to I mean, just for technical reason, we do the other side. So we start from rainbow set, we start from general Boolean algebra, and we define rainbow symmetry complex to be a downset in the general Boolean algebra. So a rainbow symmetry complex is just a downset in 2 to the s. Here, 2 to the s is just the all the set of all those are rainbow subsets of a given n color sets, the so-called general Boolean algebra. When we view a rainbow symmetry complex as a downset in a given general Boolean algebra, we will often refer to the type of this general Boolean algebra as the type of the symmetry complex. You can look back to the example again. So as I said here, these blueprints are those one element sets. And this blueprint also just one element set, but they come from different different color classes. The number of these one element sets happen to be tau 1, 3, 4. And here green prints are all those 2 element rainbow subsets. The total number of these green prints equal to tau 2, 3, 4. And also this red print, just the empty set. The size is tau 0. That's why we introduced this function tau. We need 2 other functions. Gamma tk has this very strange expression. And we also have this gamma tkj. I don't think you can remember them, but just remember that we define 2 functions, which is related to elementary symmetric polynomial. Finally, we look at a simple example, and then we will go to our main theorem. So we look at a usual tree. So a usual tree is just a one-dimensional symmetry complex, but it is a bipartite graph. So now we think of this tree as a bipartite graph. So the one part has A1 vertices and another part has A2 vertices. We know that the number of vertices still just A1 plus A2 minus 1. But this function is just tau 0 plus tau 1 and equal to gamma 1, 2. So this calculation is done for a tree, for a real tree. But we can consider a 1-2 tree. So we have defined a rainbow symmetry complex to be a 1-2 tree. If delta is a 2 pure 1-2 tree of type A1, A2, if you still remember the definition, it's very easy to see that the one skeleton of this delta give you a graph G, and this graph G must be a forest. And to maximize the number of one faces or the number of edges of the forest, this one skeleton must be a tree. That's the title here. So a maximum 1, 2, 3 just corresponds to a real tree. And that's the face number that counts the number of one faces. So the number of one faces is at most. So we have this gamma 1, 2 as an upper bound of the number of one faces of a two pure 1, 2, 3. So surely this result, we want to find a generalization, and we do get a generalization. Before stating the real generalization, we state result may be more familiar to many of you. So this is a school set pair inequality. In extreme set theory, you can see many results like this, and usually they are proved by linear algebra. So here we have parameter tkn, t less than equal to k less than equal to n, be 3 positive integers, and we have an n color set of type a1 up to an. And we consider a sequence of t rainbow subsets, and another sequence of rainbow sets, each of which has size at least k. We assume Ti is a subset of Ki, but Ti is not a subset of Kj whenever I is less than J. This is why here we say this is a school relation. Because here I and J, this is not symmetry. We only consider those pair Ij for which I is less than J. If all this, we have this intersection pattern, then we know that the number m here is upper bounded by gamma tk. So this gamma is the function introduced above. So as a simple corollary of this theorem, we know that any k pure tk tree of the given type has a size no bigger than this function, this number. That is, we can give an upper bound to the top term of the face vector of this k pure tk tree. This is an immediate corollary of this theorem. So when all the parameters are equal to 1, so our theorem 1 was first proved by Frankel in 1982. It's a very old result. So the motivation of Frankel is to study the so-called Sonic conjecture. When he was sitting in a lecture by Ping, so a very famous computer scientist, about the Sonic conjecture, and Ping raised some conjecture, basically just this theorem for all one types. And then Frankel can prove that conjecture. So a symmetric version of this result of Frankel was obtained earlier by Bolabach in the study of saturated graphs. And surely there are lots of literature on this line of research, many generalization and variants. And then we can do even more, because this theorem, I mean, this corollary basically just follows from this theorem. That's just about the top term of the face vector. But we want to have an upper bound for every term in the face vector. We can do that. So this is this theorem. So let delta be a T-collapsible rainbow symmetry complex of the given type. We assume T is less than K, and basically you can say the rank of delta is at most K. This is as a graded poset. Then we can say that the drift term in the face vector is upper bounded by this number for any j from this interval from t plus 1 to k. When j equal to k, this result says that it's about the top term. This is already predicted by theorem 1. Notice that there are some small difference between this theorem and the former theorem. Here, we say this is only a TK tree. But here, the results say we want the constraint is that this complex is a T-collapsible. The complex should be really collapsed to the empty complex. So here for j equal to k, the result is weaker than theorem 1. But now for this theorem, we can talk about basically all the phase vector, not just the top chain. And also for j equal to k equal to n, in this very special case, the theorem is already known by these four people in 2012 in their study of bootstrap percolation. And when data is the O1's type, the theorem reduced to the aforementioned result along color in 1985. So basically, you can say our theorem 3 is a colorful generalization of the alone color results. You can define some set system. We call it TK rainbow sunflower on a given n color set. I do not think we need to really look into the definition. But for this rainbow sunflower, you remember that it is a family of sets. All the sets have size k. And when the n color sets S has the O1's type, then we go back to the usual Boolean algebra. In that case, the TK rainbow sunflower is very simple to describe. It is just described here. You can take the head, the first k minus t elements, and then you take union with a t subset A from the remaining sets. So the ground set is the first n integers. So this is very much like the star construction in streamer combinatories. So you can say this is just a star. So usually you take one element as the head, but now you take k minus t element as the center of the sunflower. But this is just for the O1's type. Maybe this construction is very easy to imagine. But then for the general Boolean algebra case, it may not be so intuitive to have the idea of this construction. But anyway, when you go back to Boolean algebra, this is really easy to find. So I'll give you an example. This is a 2-3 rainbow sunflower. The type is not O1, it's 1, 1, 1, 2. So this is, still looks like a star, right? It somehow like still has a center of the star, but not really a star. The phase vector is 1595 here for this example. So this is a theorem. So for our construction, we can calculate its phase vector. So surely for the TK rainbow sunflowers, this is just a family of sets, and then you take all the subset, and then you can get a rainbow symmetrical complex over the given n color set. After some careful calculation, you find that surely the number of j phase is 0 if j is bigger than k. If j comes from this interval, it is just gamma tkj. And when j is less than or equal to t, then delta j is everything. So all the j element subsets, all the j are rainbow subsets of the given set S. So this is the, so you can now have the fixed vector of this construction. Moreover, this construction is very much tree-like. It is topologically T-collapsible. Here is a remark. So our theorem says that there is one symmetrical complex for which all the upper bounds given in the former theorem 3 are attained simultaneously. Our theorem 3 gives you an upper bound on the phase vector, but now we find that by using the rainbow sunflower, all the upper bound can be obtained. And also besides collapsibility, you may consider some other topological or combinatorial constraint like shareability, like T representability, like greedy T collapsibility, etc. So surely this is related to giving some good construction. so far we have this rainbow sunflower. We also have some variants of rainbow sunflower, but how to analyze their geometry property, this is not so trivial. I mean, even for this one, to prove that it's a topological T collapsible, this is not totally trivial. We need to have some good idea to do that. But for some other property, we have some small progress. We cannot show say much on some other constraints. We should mention that for the O1 type, our TK rainbow sunflower reduced to the very simple construction, and that it turns out that Carla already studied that construction, and he showed that the complex generated by the rainbow sunflower of O1 type is T representable, not just T collapsible. So T representable will imply T collapsible. We also mentioned one result about chromatin number. So a flat complex is nothing but the clique complex of a graph. So if we have a flat complex with chromatin number n. So here chromatin number n, surely this is some coloring constraint, but now we do not say, we do not specify the size of each color class. We only know that we have a graph which can be n colored, and then we form is clique complex. And if we know that this complex is T collapsible, and if we know that this complex data satisfy or the clique number of the given graph at the most k, then we can have an upper bound for the phase vector of the clique complex of this graph. So this is to obtain this theorem, we need to use our formal results about the T collapsible rainbow symmetry complex plus some more calculations. We can, and also our bound here is tight. We also just need to design some very special rainbow sunflower so that all the equality here will hold. Okay, we will now turn to another topic. So so far we are estimating the size of the phase vector. Now we try to show that these theorems we find it very interesting, but we want to do more. But so far we can only have this result. So we see that we have a complex, the K pure 1K tree of the given type. If we know its size attains the maximum possible value, notice that we only require it to be 1K tree. That is, only the highest dimension faces can be collapsed. And if we know that there are many K faces, the number of K faces attains the maximum value, gamma 1K. Then we know that it might be topological T1 collapsible. So this is the implication. We don't know whether or not this kind of result can hold in general. Our current proof for this result very much relies on this parameter here, and also related to our former work in phylogenetic combinatorics. So some work in totally different fields, but we need to use the work there to prove this result. So this theorem suggests that very nature question. Here is the question. If we have a TK tree, so we only know that the complex, the highest dimension faces can be collapsed. If we know in addition that the number of K faces attain the maximum size, gamma TK. So can we say that this complex is indeed T collapsible? So we really want to have a positive answer to this question, but maybe there's some counterexample. But if we have a positive answer to this question for general T and K, we can say some very good thing on oriented matrix. So I will mention very briefly. So here, for an oriented matrix or a fine oriented matrix, we can naturally generate some grid point sets. But a grid point set is nothing but a rainbow subsets. And so we can construct a rainbow symmetry complex. So in this way, we can say whether or not. So here, I mean, we have a fine oriented matrix, and then we have their top sets, and then we can go to rainbow symmetry complex. So we already proved that they are tree with some given parameter. So Tn generates an Rn tree, Ta generates an Rn tree with some parameters. I mean, you can prove the result in some special cases when R is less than or equal to 3. Here R is the rank of the oriented matrix, and or when M is realizable, when it is really comes from linear algebra. So this is the theorem. And we conjecture that in general, for every oriented matrix is an Rn tree if n is a rank R and order n. And every affine oriented matrix is an R+1 n tree for all rank R and order n. This is the conjecture. But we can count the number of faces. This is already known, but very early, 1994. So this means that if you have a positive answer to our question 8, and if we can prove our conjecture here, then we know that all the oriented matrix or the affine oriented matrix, they are really collapsible. There's something wrong with my computer, maybe too hot. The last part of my talk will be related to sparsity. So far, I end the part on collapsibility. Maybe I skip the technical part. I'm very sorry, my computer doesn't look there, so my screen is shaking, so somehow very difficult for me to continue. So maybe I should go quicker. So let's ask an n-color set of type A1 up to An, and we can construct rainbow symmetry complex on this n-color set. We can say how sparse. We define some sparsity measure of the rainbow symmetry complex. This is this data. So definition is still technical, but I should say here. So we are talking about phase vector, but for rainbow symmetry complex, we have another definition, so-called rainbow phase vector. This is somehow a refinement of the usual phase vector of a symmetry complex. Because we now have a rainbow symmetry complex, we can count various kinds of margins or local margins, besides just look at using the dimension as the measure of the so-called local area. We can have many other kinds of restriction and projection. And in this way, we can define a rainbow phase vector. Maybe I also skip the definition here. So here, this formula tells you that when you go back to the usual symmetry complex for the O1 type, the phase vector, this is the usual phase vector, and the rainbow phase vector, they have very simple relationship. Basically, if you have the rainbow phase vector, you can recover the phase vector. So this is the refinement of the usual phase vector. So we use this rainbow phase vector to define sparsity, various kinds of sparsity. And then we have the theorem. So this is about the consistency of the phase vector at the different levels. Just like the Kruskal-Kartner, theorem tells you that if you know the number of 5 faces is 100, then the number of 4 faces cannot be too small. Here, we do not look at the phase vector, but the rainbow phase vector, so we have some other kind of constraints. But here we do not have any categorization. We have some consistency relationship. So here we say that if delta has a sparse property, oh, sorry. So for the consistency, maybe I should say these results. This is related to the consistency. And we have the conjecture. So for QKD, we must have QK plus 1D. This result, if it's true, this is similar to Kruskal-Cartman. And we verify the conjecture only for D equal to 1. But this result says that sparsity and collapsibility has some relationship. This is the content of this theorem. So this result says that if delta has a sparse property Qn1 bar over S, then if we know that it's a 1 and 3, this is a collapsibility. So if and only if it has a sparse property Q21. So under this condition, so the total number of edges, if we know it is equal to this number. So this is the condition Qn bar 1. Then the sparsity requirement 1 and 3 is equivalent to the sparsity condition Q21. So this is the assertion of this theorem. Surely we try to develop some more connection between sparsity and collapsibility, but so far this is our most meaningful result, non-trivial result. And then we try to compare the study in these two lines. So as I said before, we have the for sparsity, we want to establish some consistency result. We have the conjecture. And we verify the conjecture in some special cases. And then we have, if we try to find a parallel to this conjecture, we are not brave enough to say this is a conjecture. So far, we say this is a question. So assume that because we already defined some operation, projection, restriction. So you know that the various local shadows are TK trees. Whether or not this implies that delta itself is a TN tree. So this is the basic idea of this question. Somehow we want to develop an analog of this conjecture. We believe that this conjecture should be true. And so this is a parallel to the earlier conjecture. Maybe I should end the talk here. So I can talk more. Somehow I am staying home for more than 2 weeks due to the COVID panic, and my computer are not very good here. So somehow my screen is shaking. So I mean, the last few slides I'm seeing some collection to rainbow inclusion match. Maybe I mentioned these facts. So our study here, so we are trying to find an upper bound for the phase vector of a collapsible rainbow symmetry complex. How to find the upper bound? Basically, this is equivalent to find the maximum size of a unipotent submatrix of a rainbow inclusion matrix. This is the same problem. If I state the problem with this language, you can say more. You can agree more with me that this is a study on algebraic combinatorics, because inclusion matrix is very correct topic in algebraic combinatorics, and also unipotent submatrix. Also, this size surely has the rank of the inclusion matrix as a upper bound, maybe not a good upper bound. But that's why in the talk on the first day of these workshops, so one of my co-authors, so Yan Zhenxun, was talking about rainbow inclusion matrix. That's also related to this work. So that's an interesting story. So in 2024, in the study of phylogenetic combinatories, so partition system displaying some phylogenetic tree, in the study of that kind of concept, we have a conjecture. And later on, maybe only very recently, we find that this conjecture is a very special case of a result that by did for people. So I already mentioned their theorem in the very beginning of this talk. So their result already much stronger than our conjecture in 2020. But this theorem or this conjecture, a special case of this conjecture, when t equal to n-1, the conjecture was proved by Frank and Parr, and also by ourselves. And both proofs are very short after knowing the rank of the inclusion matrix or the theta matrix of the general Boolean algebra. If this rainbow inclusion matrix, we know that the rank is just the gamma n-1n, then we can prove this special case of this conjecture or even special case of the result of the theorem by these four people. But I want to mention that there are several different proofs to this even very special case. So the one even simple proof can be seen by calculating the homotopy type of the general Boolean algebra. This general Boolean algebra has a very easy shading process. This is indeed so-called strong shadable. So if you know, if we have this, you know that it is strongly shadable. You know this partition here. This is an interpartition of this general Boolean algebra. Then you know that it is strongly shadable, and then by a easy result in topological combinatories, then you can get something on the homology of the general Boolean algebra. Then easily you get this rank. So this is just a remark. But even this very special case, I think we have the paper by Frank and Parr will be published very soon, because in their archive paper, they already acknowledge the help from the referees. Okay, thank you very much. I think I should end my talk here.
Okay, thank you very much for a very interesting talk. Any questions to the speaker, please? What is exactly the picture as the last slide?
Oh, because I find that 2022, then in 2019, that's 4 years ago on the same day. So
really,
March
the
25,
same day.
The same day, and on our campus in our new building. So a seminar by I think you can recognize who is this guy.
Okay.
Also the speaker on the first day.
Right, yeah, that is true. Yeah, he was a speaker of the first day, and it was very interesting to talk about inclusion matrices, right? Yeah.
Mm-hmm.
Mm-hmm. Well, okay. Any questions?
May I?
Yeah, sure, Alexander, please. Yeah, sure.
First of all, Yaokun, thank you very much for very interesting talk. And I should say one thing. Of course, I deal many times with the classical symmetric function, sigma. But in your talk, you introduced a new one, you called tau. It was quite surprising for me, very simple definition, but in the same time, very useful equipment. For example, to recognize forest and also to recognize high-dimensional version of forest. Of course, it's quite interesting to use this kind of function to investigate another combinatorial structures. And I will try also sometimes to use it in my investigation. Thank you very much.
Yeah, thank you, Sasa. But we use sigma for elementary symmetric polynomial. Maybe that's somehow standard. We are using a variant of the elementary symmetric polynomial. So tau is not a symmetric polynomial. So let me see.
Some modification. Yes, this sigma gamma also comes from this. Okay.
So sigma is the elementary symmetric polynomial, and tau is a very close relative of elementary symmetric polynomial. Yeah.
But quite convenient.
Yeah.
The reason quite convenient to use.
Mm-hmm.
Well, I have a very simple question concerning an example which was given you during your talk. It was example of colorful complex right here. So I just wondering, would you please explain me just what are colors there exactly? I mean, as that example. So it was a
you mean our theorem on the
no, a little bit further.
You are talking about our theorem or just the definition?
Not definition. No. I'm asking about example. It was example of a colorful complex. Well, with faces which are colored, and you investigate it and show the numbers. Yeah, this one. Yeah. So yeah,
here the color
so
just given to the.
What does it mean? What does it mean? Face vector.
For example, the number of 0 faces, just the empty set. So that's 1, right?
Right, yeah.
You only have the empty set. And for the number of 1 faces, that's size 1 faces. Mm-hmm. So 1, 2, 3, 4, 5. We have 5.
Right, yeah.
1 faces.
That is the way. Oh, I see.
And also,
I see.
Yeah.
I see. That is the way. Okay.
So 2 faces, the number of edges, and then 3 faces, number of triangles.
I see. Now understood. Yeah. Okay. Thank you. Any other questions? Well, if not, then let us thank Yaokun again for this very interesting talk concerning very interesting combinatorial subjects. So thanks a lot. Yeah.
Thank you.
Well, okay. Our next